Hi guys, in this video we'll take a look at exponentials and gradients, the gradient of exponentials with base e, examples, and then we'll finish with a summary.
So how can we interpret the gradient of an exponential function? We know that the gradient of a straight line is constant. So if we have any straight line, which in general is of the form y is equal to mx plus c, then the gradient is constant, and m will be the constant gradient value. However, we usually find in mathematics the gradient of a function changes with x. So if we consider different x values, say here at x equals minus 4, in here at x equals 0, and up here at x equals 5, then we will find the gradient at each of the corresponding points on the curve, the gradient is changing with x. We would like to consider the gradients of various exponential functions. At each of these points on these exponential graphs, we'd like to know the gradients in general. The gradient of an exponential function has interesting properties and is closely related to the original function. So the original function, let's say, is of the form y is equal to a to the x. Then we are able to relate the gradient, as we plotted here, to the original exponential function. But we need to see exactly how we can do that. So what is the gradient of exponentials with base e? We can investigate how the gradient of an exponential function at a point depends on the function's value at that point. Suppose we have our exponential function y is equal to 2 to the power of x. Then we can consider different values of x and then corresponding y and corresponding gradient. Let's have for x minus 2, minus 1, 0, 1, 2, and 3. Then for corresponding y, we're going to have 0.25, 0.5, 1, 2, 4, and 8, using the function for y as 2 to the x. And it turns out that the gradients that correspond are 0.173, 0.367, 0.693, 1.386, 2.773, and 5.545. And it turns out that we can relate y to the gradient by taking y and for each value multiplying by the constant value 0.693. We can see that the gradient of an exponential function at a point is just a multiple of the function's value at that point. We take, for example, our 0.25 and our 0.5, these are the first y values on our list. And if we multiply both of these by the constant value 0.693, then we are going to get 0.173 and 0.367. And these are the first two gradient values on our list. And we can do this all the way down for all of our values. So in general, the gradient is always a multiple of 0.693 of the values of the function y equals 2 to the x. We can use the gradient calculated at various points to plot a curve of the gradient next to the curve of the original function. We can take our original function, which is in this case y equals 2 to the x, and then we can examine the gradient, which everywhere is given by 0.693 times 2 to the x. And this follows suit with our points we calculated for corresponding to our x values between minus 2 and 3 above. Now, as the base increases, the multiple corresponding to the gradient increases as well. If our original function was y equals 1.5 to the power of x, then the gradient corresponding to this is going to be 0.405 multiplied by 1.5 to the power of x. Similarly, if our original function was y equals 1.7 to the power of x, i.e. the base has increased from 1.5 to 1.7, then correspondingly the multiple increases. Our gradient in this case is equal to 0.531 multiplied by 1.7 to the power of x. Between 2 and 3, the gradient changes from always being smaller than the original function to always being larger than the original function. Let's say we have again our original function being y equals 2 to the x. Then as we saw, the gradient was 0.693 multiplied by 2 to the power of x. And if we have our original function being instead y equals 3 to the power of x, then it turns out that our gradient in this case is going to be 1.10 times 3 to the x. So in the first case, our multiple is equal to 0.693, which is strictly less than 1, and in the second case, the multiple is equal to 1.10, which is strictly greater than 1. And because as the base increases, the multiple increases, there is a base between 2 and 3 for which the multiple is exactly 1. And the base at which the multiple becomes 1 is denoted by e. It turns out that e has an approximate value of 2.71828 and so on. If y equals e to the x, then this means that the gradient is equal to 1 times e to the power of x. The multiple is 1. So we have our original function y equals e to the x, and our gradient function is also e to the x. So how can we interpret the function e to the x? The graph of y equals e to the x has the special property that its gradient is also equal to e to the x. For the function y equals e to the x, the gradient is also e to the x. So we have our original function, which is y equals e to the x, and simultaneously the gradient is also y equals e to the x. We can also find expressions for the gradients of exponential functions of the form y equals e to the power of kx for some constant factor k. It turns out that if y is equal to e to the power of kx, then the gradient is given by k multiplied by e to the power of kx. If we have, for example, y equals e to the power of 2x, then our corresponding gradient is going to be given by 2 multiplied by e to the power of 2x. Similarly, if y is equal to e to the power of minus a half x, then the corresponding gradient will be minus a half e to the power of minus a half x. The shape of a curve of the form y equals e to the kx is similar to that of y equals e to the x, with the steepness of the curve determined by the constant k. So this is the graph of y equals e to the x, for example. It passes through, of course, the point 1, as always, and the gradient is given by e to the power of x. But then if we sketch, for example, y equals e to the 2x, but we notice that it's steeper. And this is because the gradient was given by 2e to the power of 2x. Let's take a look at some examples. Our first example asks us to sketch y equals e to the x and y equals e to the 2x on the same axes. Our first step is to sketch the shapes of the graphs individually. They have around the same shape, except e to the 2x is steeper. So we have this for y equals e to the x. Again, it passes through 1 as always. And then we have this for y equals e to the 2x. Again, passing through 1. Our second step is to find the graph transformation relating them. If we let our f of x be e to the x, and we let g of x be e to the 2x, then we note that our g of x, which is equal to e to the power of 2x, is just the same as f of 2x. And therefore we can use this to, for our final step, sketch them on the same axes. We have our x and our y axes. They both pass through the y-axis at 1, but our y equals e to the x will start slightly higher and be less steep, and our y equals e to the 2x will start slightly lower but get steeper. So we have our y equals e to the x below for positive x values, and our y equals e to the 2x for above for positive x values. Our second example asks us to find the gradient of y equals e to the 2x in terms of x. Our first step is to recall the gradient of a general function y equals e to the kx. If we have our y as being equal to e to the power of kx, then this means that our gradient can be found by taking k multiplied by e to the kx. Our second step is to substitute the value of k required into the formula. We have that k is equal to 2 for our corresponding exponential. Therefore, having y as being equal to 3 lots of e to the power of 2x, we're going to get that the gradient is going to be, well, firstly we have our 3 outside. This is maintained in the gradient, and then we multiply by a value of k, that is 2, and then we have our e to the power of 2x. Our last step is to write down the gradient of the exponential. For our y, which is equal to 3e to the power of 2x, the corresponding gradient is 6e to the 2x. Our last example asks us to find the exact value of the gradient e to the x multiplied by e to the x plus 1 when x equals 2 to 3 significant figures. Our first step is to expand the bracket. We have e to the power of x multiplied by e to the power of x plus 1. We can expand this as e to the power of 2x plus e to the power of x. Our second step is to recall the gradient of a general function y equals e to the kx. If we have our y in the form e to the power of kx, then our gradient is going to be k multiplied by e to the power of kx. Our third step is to split the resulting sum into 2 separate functions. We have our e to the power of 2x plus e to the power of x. And we can split this into our first function, e to the power of 2x, and separately our second function, e to the x. Our fourth step is to find the gradient of the first function. The gradient of our first function, which is e to the power of 2x, because we have k equals 2, is going to be 2e to the 2x. Our fifth step is to find the gradient of the second function. Our second function is e to the x, so the gradient of e to the x, which corresponds to k equals 1, is going to be e to the x. Our sixth step is to write down the full expression for the gradient of the original function. The gradient for our original function is going to be, by adding them up, 2 lots of e to the power of 2x plus e to the power of x. All we have done is to take our original function as a sum, worked out the gradient of each one, and added up the results. Our sixth step is to substitute in x equals 2. We're looking for the gradient when x is equal to 2. So the gradient is going to be, by using our above gradient function, 2 multiplied by e to the power of 2 times 2 plus e to the power of 2. And this gives us 2e to the power of 4 plus e to the power of 2. Our seventh step is to evaluate the gradient at x equals 2 to 3 significant figures. When x is equal to 2, we have our corresponding gradient as 2e to the 4 plus e squared. Using a calculator, this is equal to 116.585 and so on. And this is equal to 117 to 3 significant figures.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together, let's make A-level maths a walk in the park.